Alright, thanks for the opportunity to present my research. My talk is Apatite as an indicator of porphyry fertility in the Northparkes district, and I'll just take a moment to acknowledge Seb Meffre, Dave Cooke and Jeff Steadman, as well as John Hoy at Northparkes. Just a quick presentation outline. I'll go through some sample locations, an overview of Apatite, the methods I've used, and then some results. So spatial variation of altered Apatite, Apatite mineral chemistry, some definitions of primary versus hydrothermal apatite, and then the key thing, apatite as an indicator of porphyry mineralisation. The Northparkes district is located roughly 350 kilometres west of Sydney, or about 15 kilometres northwest of the town of Parkes in central western New South Wales. Numerous economic and sub-economic porphyries within the district. The major mining operations E22, E27, E48 and E26 occur along a roughly 4 kilometre northwest-southeast linear. Most of the sampling was undertaken at E26 with a few at E48 and lots taken down at E44, which is a long-term prospect that's seeing renewed interest by Northparkes. So 34 grain mounts overall, 600 cathodoluminescent images, and then subsequent microprobe and laser ablation analysis on the same grains, with a few being discarded along the way due to not being suitable, and samples taken from a variety of economic and sub-economic intrusions across the district. So apatite is actually a group of about 40 mineral varieties. At Northparkes, they're dominantly fluoroapatite. They have the general formula calcium, phosphate and fluorine, but there's about 48 things that can substitute into there. There's a broad range of coupled substitutions, and apatite's a bit of a geochemical sponge, so it's been a nice challenge. So the methods used in this research: manual separation by panning and hand picking, mineral liberation analysis of grain mounts, morphology, zonation and inclusions in apatite grains are assessed using colour cathodoluminescence, backscatter electron images, as well as optical microscopy, then microprobe and laser ablation, with the works carried out in that order from least destructive to most destructive. Mineral liberation analysis was primarily used to enable targeting of the same apatite grains using different analytical methods. So I'd capture a backscatter electron image as well as the MLA image, overlay them on each other and develop a map similar to the one on the right hand side. They're actually quite high res images, and that one's just zoomed out a fair bit. Applying fake Cartesian coordinates enabled me to scan to the grains of interest. In particular, I targeted grains that were aligned parallel, had the C-axis aligned parallel to the surface of the grain mount or perpendicular to the analytical beam, whether that's electron or laser. Colour cathodoluminescence was used after some work by Farhad Bazari in 2016 to examine whether the same variations occurred at Northparkes. So on that basis, the larger colour CL image with the complex internal zonations and brighter colours is interpreted as being a hydrothermally altered or recrystalised apatite grain. You can see in the backscatter electron image small inclusions of what's likely to be monazite within that grain, whereas the grain at the bottom of the screen is interpreted as being a magmatic, much happier in terms of internal zonation, and a relatively uniform blue colour, which is quite ubiquitous at Parkes for least altered samples. Once the colour CL images were captured, we moved over to the microprobe to analyse the same grains, and noticed that some grains had depletion in the light rare earth elements, particularly cerium and neodymium, and concurrent depletion in calcium and enrichment in strontium. We postulated whether that's a product of plagioclase destructive alteration, but that's a bit of an arm wave. So to tie the two together, the colour cathodoluminescence and the mineral chemistry, we went back through and carefully looked at each grain and determined that green to yellow luminescence is related to that elevated strontium and manganese with depletion in calcium and the light rare earth elements. The dark brown luminescence is related to high magnesium and iron, from what we could determine, and from that we figured that the ragged green luminescence is a product of hydrothermal alteration and recrystalisation. Then broke it down to looking into magmatic apatite, so those with the blue colour CL response, and looking at their mineral chemistry. In this case it's laser ablation data. As you can see, there's very little variation between apatite from mineralising intrusions, which are quite well defined at Northparkes, and those from barren intrusions. So even though there's some variation, in most cases it overlaps, so not a lot to be told from magmatic apatite, unfortunately. The good news is that hydrothermal apatite is a completely different case. So increases in sodium, manganese, depletion in arsenic, enrichment in strontium, and depletion in tungsten were all indicative of mineralisation at E26. Tungsten's an unusual one, and so is arsenic because it appears to be case dependent, but need to do more testing before we can make any robust statements on Northparkes as a whole, but at E26 this is the case. Taking this one step further, we looked at two samples of a mineralising intrusion from E26. The only difference between the samples was alteration intensity. The more altered samples had depletion in yttrium and the light rare earth elements, both in mineral chemistry and in assay, but the difference was far greater in the mineral chemistry, so a nice indicator to be pulled from apatite there. Another good indicator was the strong positive europium anomaly that was observed in apatite, while difference in whole rock assay was relatively minimal. Other elements of interest were sodium, arsenic and tungsten, which had inverse relationships with whole rock assay. Looking at that low sum of light rare earth element trend in greater detail, you can see that at E26 there's a depletion in arsenic and an enrichment in sodium and manganese that's concurrent with that depletion in the light rare earth elements, which is characteristic of the altered apatite there. Nearly opposite trends at E44, we see an enrichment in arsenic and a depletion in sodium, making it pretty apparent that these need to be considered on a case-by-case basis other than the light rare earth element depletion. Looking at the light rare earth elements in a little more detail, you notice that the strong positive europium anomaly that occurs towards the carapace of E26 is proximal to one of the higher grade ore zones, which is similar to a finding of Jerry and others at Olympic Dam, which needs a little bit more research to figure out why that is the case. In regards to all the other low sum light rare earth apatite or altered apatite across Northparkes, there was majority negative europium anomalies and little to no enrichment in the mid rare earths, which builds a case for this being more of a case-by-case basis, but as well raising the question, is this europium anomaly particularly related to high-grade ore zones? Put together this schematic for vectoring potential of altered apatite at E26 as a case study. All apatite towards the cupola at E26 are recrystalised, so they have that complex colour CL response, bright yellow greens, and their rare earth element depleted. So if you're lucky enough to be doing an air core program and want to do some apatite sampling from some sap rock, if you return either low rare earth element concentrations or internally complex colour CL responses, you're probably drilling on top of a porphyry, so it has some implications there. So in conclusion, light rare earth element depletion in apatite at Northparkes is characteristic of hydrothermal alteration, particularly towards the carapace of the mineralising intrusion at E26, along with that strong positive europium anomaly which occurs near the high grade zones. The mineral chemistry definitely affects the cathodoluminescent response of apatite, and it has significant potential as an indicator of porphyry mineralisation at Northparkes, particularly if you're sap rock sampling using air core, and you can pull those apatite grains out, and if you see depletions in the light rare earth elements or complex colour cathodoluminescent responses, potentially you're on the money, and you should ask the boss for a little more coin to sink a diamond tail behind that EC or RC hole. Anyway, thanks very much for your time, and sorry I can't be there to answer questions, but I'm sure Seb will have a go at answering them for me. Alright, thanks very much.